Welcome you all to the 12th talk of the talk series 1920 conducted by System Society of India Trivandrum chapter. On behalf of System Society of India Trivandrum chapter, I would like to extend a heartfelt welcome to our today's speaker, Sri M.V. Dhekane sir, Distinguished Scientist, retired ISRO. I would like to introduce today's speaker now. I consider it a privilege to introduce today's speaker, one of my guru and the father of ISRO launch vehicle autopilot systems, Sri M.V. Dhekane sir. Sri Dhekane sir, after completing B.Tech and M.Tech from IIT Bombay, joined VSSC in 1983. Sir has significantly contributed in the areas of mathematical modeling of launch vehicle dynamics, control and guidance design, onboard software development, navigation guidance control validation, and mission analysis for various ISRO launch vehicles starting from ASLV. He held various posts in ISRO, Director IASU, Associate Director VSSC, Chief Controller VSSC, etc. He was Satish Dhawan Professor at IAST. He is currently conducting a course on launch vehicle modeling and autopilot design at ADYUPU Pune. He is an active member of various technical reviews forums of ISRO presently. He has authored nearly 35 technical papers, and Sir is a life member of various professional bodies like SSI, ASI, ISSC, etc. Sir is recipient of so many awards. Few are ISRO PSLV Team Award, ISRO Merit Award, ISRO Performance Excellence Award, and he is Fellow of Indian National Academy of Engineering 2018. I welcome Sri M.V. Dhekane sir to deliver the talk on seminal work on control systems. Sir, now the floor is yours.
Thank you, B.V. Sebastian. All my dear colleagues, Dr. Jaykumar, Geeta, Asha, Dr. Patil, and then Dr. Pradeep from Professor IISc, and all my colleagues. So today's topic I have chosen is seminal works in control systems, how control ideas shaped everything from rockets to robots. So basically, what is seminal work? It's a piece of research, writing, or an art that is highly influential and foundational in its field. New ideas, methods, perspectives that shapes future developments. So these seminal works basically laid the groundwork for every modern automated systems. They show the power of innovation over decades and inspire everything from satellites to smart homes. So basically there are many papers. I mean, if you go through control systems, journals, thousands and thousands of papers you'll come across. But then there are certain milestones which we will be looking at, which really have laid down the mathematical foundations. As such, if you Google, they say that automatic control system dates back to about 2000 years. But then feedback or closed loop automatic control, these things, I mean, milestones among these things are, one is the temperature regulator of a furnace attributed to Drebel 1620. Then James Watt, I think many of us learn about those things even in our school days, like flyball governor regulating the speed of steam engines. But then subsequently in 1868, James Clerk Maxwell, in his paper on governors, explained some instabilities. So one can talk about many such things, but really the mathematical foundations have been laid down by, for control systems over last 100 years. So how does the whole thing evolve? So World War II, rise of military equipments, radar targeting systems, and various instrumentations, oscilloscopes, analog computers, these things started appearing in the early 40s and all. So the need for the era was the feedback system development for electrical networks, telecommunications, and so many things, which needed stability guarantee. Now, all of us who have gone through basic control systems course, we know that we start with basic understanding about a system, the transfer function, poles and zeros, its meaning, like poles in right half of a system makes the system unstable, and so on. Routh-Hurwitz criterion to find out from a polynomial whether the poles are in the right half, and so on. Now, the advanced, the methods which got developed in 30s, 40s and all are basically stability in feedback by Nyquist, then the gain phase trade-offs, that became vital paper by Bode 1940, and root locus techniques, Evans root locus techniques. So till this time, probably there were no systematic way to analyze stability under feedback before deployment, which means that we have some open loop system. We have designed certain gains or compensators, and we are going to close the system, which is a feedback loop. Now, before we close the loop, we should understand whether the system is going to be stable or not. And these seminal papers written by Nyquist, Bode, and so on, they really brought out how the things are to be analyzed. Like many of us, we know about the Nyquist criterion. Like if we have number of unstable poles in the open loop system, say P number, then, and if we go for a polar plot, like when evaluating the open loop transfer function from for j omega from 0 to infinity, and then right half covered in a closed form, we can get this closed loop system stable if we get that particular equation z is equal to n plus p. So all these things basically gave an idea how by graphical methods one could derive the stability of the system. Bode's integral theorem is another foundational result in control theory that provides deep insight into the limitations of feedback control. Sensitivity function, one interesting thing people read about is Waterbed effect. Like gain reduction in one frequency range must be compensated by gain increase in another, particularly when the plant has unstable poles or right half plane zeros. And the right half plane zeros, how they limit the required, rather achievable bandwidths or achievable robustness, all these things are brought out nicely by Bode's paper in 1940s. Root locus is again another graphical method where from the open loop transfer function roots, we are able to get an idea about the closed loop poles as a function of, say, gain parameter. Gain changed from 0 to infinity. The poles, they will migrate and they will eventually go to zeros as the gain goes to infinity. But then for particular design gain, we will be getting some, the required pole formation, which basically defines our system. Now, once we entered 50s, 60s and all, control became more practical. More and more industrial plants, automation, manufacturing, all these things started coming up. Early space race, like 1957, the first satellite went into space, and then the space race started. That was driving the advances in navigation and tracking. So the need for the era was control system needed to react in real time for industrial automation and aviation. And then various problems like sensor data, which has got noise, data was not clean. How do you extract the correct signal out of it? And also the control systems, which in a classical control way, PID controllers came into picture. So in 1942, Ziegler and Nichols have introduced tuning rules to set the suitable parameters like Kp, Kd, Ki. And these techniques became very popular, and they started being used widely in industry. Kalman filter is another interesting development. 1960, R.E. Kalman had written that seminal paper. So this Kalman filter is a recursive algorithm to estimate the state of dynamic system from a series of noisy measurements, which produces an optimal unbiased estimate. And Lyapunov theory. Now the interesting part again is that Lyapunov theory was brought out in 1892, but its actual application started coming up in 50s, probably 50s, 60s, and so on. And then it became a very important tool to guarantee the stability. Many times such things happen, like mathematical developments take place much early. Their applications come up after some 30, 40 years. Another beautiful example is the pseudo-inverse, that Moore-Penrose pseudo-inverse. In 1920s, Moore had proposed that pseudo-inverse concept for rectangular matrices, and its application came up only in 60s. PID, as you know very well, proportional control defines the bandwidth, speed of response, and reacts to the present error, whereas integral term corrects past errors and reduces steady state error, whereas derivative predicts future error and improves the damping. So this PID controller again has been being used in many control systems, especially for chemical plants. It became very handy, and PID tuning was integral part of the chemical plant control. This is just a block diagram for Kalman filters, which gives best estimate. Now, application of Kalman filter is enormous. I mean, almost every field we are able to see that, right from navigation and control, target tracking, robotics, signal processing, computer vision, like even finger print analysis, handwriting, and many things. One can get the data, update it with the prediction, and then with the noise and all, we can get into a clean data, especially for fusion of sensors. In our aerospace, if you look at the attitude data with multiple sensors, we have to have, I mean, we are using Kalman filters for extracting the best estimate, especially for position and velocity. The accelerometer data is augmented by GPS data, and then again Kalman filter algorithms used for getting the best estimates. Lyapunov stability problem involved determining the stability of dynamical systems, etc. Moving to 60s and 80s, digital computers became stronger, cheaper, space missions became more complex, mathematical control theories were matured, dynamic programming came into existence. I mean, its applications started growing. So, especially for rocketry, these high fuel costs and optimal control, that became very important thing, becomes a very challenging thing. So all the spacecraft, missiles, satellites needing precise control. And here, matrix methods with state space analysis, state space models, which formalized full system knowledge rather than surface outputs, and the LQR kind of techniques. These things became very popular. So state space representation becomes important when it provides comprehensive, flexible, and scalable way to model and analyze dynamical systems, especially multi-input, multi-output systems. We can go for state space. And then once you define these dynamics in this form, x dot is equal to ax plus bu, y is equal to cx plus du kind of form, one can go to development of transfer functions, analysis, and for using matrix algebra, which enters many mathematical tools. All these things become much easier. And especially it was useful for expressing the MIMO systems. The LQR techniques, LQG, LQR, then loop transfer recovery, LTR techniques, all these things became operational in this field, I mean, this era. Now, now we entered somewhere between 80s and 90s, industrial robotics started rising. Computer power had increased, sensors advanced, and many widespread use of computer-aided control system design tools had come up. So basically the need for developing new methods and all were again based on the control of plants with unpredictable environments. We have to model inaccuracies, disturbance rejection, robustness for the controllers to be established. All these things gave rise to new methods, new advanced methods like H infinity, adaptive control, model predictive control, like that. So H infinity, of course, you know that it is an advanced control method designed to achieve robust performance and stability in presence of model uncertainties and disturbances. Whereas the adaptive control itself adapts itself for the variation in the controlled system's dynamics or external disturbances. Like you have a process and then the input to the process, output to the process, these things are being used to estimate the update in the control parameters, and that way it changes the controller and then it goes on. So if there are some changes in the process, that gets absorbed or gets estimated and then gets into the control parameter change. Model predictive control again predicts future behavior and optimize control actions. As we know that launch vehicle guidance is an excellent example for these things. Interplanetary missions, Mars, moon landing, where the future behavior probably we may have to predict and take certain actions. Now, last decade of 20th century, it was like explosion of computers, AI techniques. AI techniques started emerging basically, neural networks, expert systems, etc. Already high precision sensors and actuators were in the picture, microcontrollers, embedded systems. There was a boom. Now, typically one can even would have come across fuzzy logic in washing machines. Now, all these things, we were getting into more and more intelligent systems. Okay. So, and just the system models did not remain just linear. Various nonlinear models directly could be or had to be controlled. So one can come across Zade's paper 1965, Utkin's paper 1960, fuzzy logic, sliding mode control, then optimal trajectory planning, etc. These papers had come up in 60s, 65, but their applications started coming up in this decade. Like fuzzy logic controllers, these use linguistic terms. If fuzziness is included in the algorithms, and that tools to map inputs to outputs, allowing them to adapt to changing conditions. And it was really a major breakthrough in the field of artificial intelligence. Sliding mode control is another nonlinear control method that alters dynamics of a nonlinear system by applying discontinuous control signals. Now, that is again another thing which became very crucial, very useful for many systems where we could demonstrate robust action through sliding mode control. Optimal path planning. Now, those who have been working in all rocketry, that's not a new subject now, because right from lift off till end of the trajectory, placing the satellite into the orbit, like calculus of variation is used, and then the trajectory optimization. All these things are, I mean, part of our day-to-day business nowadays. Multidisciplinary optimization, MDO, is emerging. So all these things are like part of our regular work nowadays. Oh. So now beyond 2000, what are the things? Internet of Things, wireless communication, quantum computing, AI and ML, all these things started emerging. Now I think AI and ML has become part of syllabus in many engineering courses. For drones, satellite constellations, all these things, they again needed some new developments. So like AI models, distributed control, quantum computing, all these things, quantum control, all these things started becoming as a regular feature. So these are now new milestones in the last 10-15 years probably. Like a neural network, all of you know that it is an artificial mathematical model used to approximate nonlinear functions. So you have some input layer, hidden layer for computing, and then the output layer. So again, neural networks became useful for facial recognition, handwriting recognition, general game playing, and so many things. Quantum control plays another, I mean, very, very important, crucial role now in manipulating quantum systems such as atoms, molecules, qubits with high precision to achieve desired outcomes. So basically, it combines the principles from quantum mechanics and control theory that gives you the quantum control. Now, these are all emerging fields now, along with maybe another next decade, 2 decades, we will be seeing self-healing systems detect, adapt, fix autonomously, explainable control decisions like critical for safety critical AI, artificial intelligence development. For quantum computers, some quantum resilient control will be developing now. Biohybrid control. There are now n number of fields which are emerging, and I think this journey will continue for many decades now, transforming the entire control things into AI controlled systems probably. So with this, I think I will end my presentation. So thank you all for listening patiently. I just tried to touch upon important works, but no way it is exhaustive. There are many important and very crucial papers. Probably I would have missed nonlinear systems and so many things. So I think this, I just thought that will project it in this forum so that those who are interested in looking into the history of control systems can work on these things and then look for some new ideas. Thank you.
Thank you, sir. I'm Mercy this side. Good evening, all. May I request the speaker to kindly answer 1 to 2 questions in 5 to 10 minutes from the chat box, because it's already 8:32.
Dr. Shastri, can I have a question?
Yeah.
Dhekane sir, it is so nice that you have touched upon very many topics. With aerospace, we just want to find out whatever algorithm we use, the convergence is very important, whether it will
Yes.
converge or not.
Yeah.
So, do we have any idea about these advanced methods? To converge, can we have a mathematical proof that the convergence is guaranteed? If it is not guaranteed, I think it's difficult for aerospace and human related issues. So, could you kindly elaborate?
Yeah, you are right. Actually, mathematical proofs for everything is very important, and many times these methods, they don't come up with very clean mathematical proof. Like neural networks, how they will work, and what is the mathematics behind it. There were research for decades. So now also many papers come up for talking about mathematical proofs.
Yeah.
So this is one important thing.
AI.
Yeah. Pardon?
Continue.
Anybody else who are asking one more question can be answered maximum? Okay, due to paucity of time, we are not able to completely answer all the questions in the whatever is asked. Remaining questions shall be answered in person later. So let me enter into my responsibility of thanking the speaker of the day. It was indeed a great time we have spent with you, sir. At the outset, let me thank the speaker on behalf of the Executive Committee of SSI. On behalf of all present, I extend my heartfelt thanks to Sri M.V. Dhekane, distinguished scientist, retired former director ISU, for sharing such insightful perspective on seminal works in control design. Your depth of knowledge and passion for the field has truly enriched our understanding. We are grateful for your time and for inspiring us with your contributions to science and engineering. Your talk provided a rich overview of the foundational contributions that have shaped the field from classical control design to modern advances in robust, adaptive, and optimal control. Your skill highlighted the milestones achieved by pioneers like Bode, Nyquist, and Kalman, while also connecting those contributions to current trends and real-world applications, namely fuzzy logic, artificial intelligence, etc. We truly appreciate the depth of knowledge and clarity you brought to this important topic. Thanks to one and all who has attended the lecture wholeheartedly. This is Mercy signing off. Thank you.
Has cut me down mercilessly. Okay, thank you.
Thank you so much, sir.
Thank you, Dhekane sir.
Thank you. I think it was very interesting.
Really very good, sir.
Many of you have gone through these things during their